Sì, sì.
Sì.
Very good. Okay, so what are we looking at here? We're looking at the Semenov system, okay? Or the thermal explosion system. This is what we had started to look at. Essentially, let me just switch on this thing here. If you remember, we were actually looking at a system of this form. We were monitoring the temperature, okay? Let me remind you, this is a closed vessel of volume V, okay? With a production of heat and then heat loss by cooling, okay? So there is a reaction happening inside here, okay? A reaction, an irreversible one-step reaction that follows Arrhenius kinetics. So it's exponentially related to temperature, clearly, okay? So remember, this exponential is crucial. It's very, very important in combustion, and we have very high sensitivity to temperature as the activation energy increases, okay? So it has essentially the property of releasing all of the reaction rate closer and closer, okay, to the maximum temperature, which, for example, is the adiabatic temperature. In this case, it won't be because we are essentially losing heat, okay? And this is heat lost by convection through a cooling system, or a cooling jacket, how it's called. So if you want to monitor the rate of change of temperature, well, you have to essentially have an equation of this kind, where you have on the right-hand side a positive and a negative, okay, source term, okay? So the positive source term related to the heat release by the reaction, and the negative term through the heat loss to the surrounding. What we have seen as a very basic way of analyzing this system is simply the graph, okay, of these two functions, okay, which you can see here. So we're not really doing any integration, okay? We're not integrating the, okay, we need another equation here for this, for the concentration of the reactant. But in any case, if we graph, okay, Q plus and Q minus, we can see the properties, the stability properties of the system, okay? And for example, whenever these two graph intersect, okay, one will be the exponential, okay? The other one will be the linear function, Q minus. When they intersect, clearly Q plus is equal to Q minus, and you have an equilibrium point, okay? And not only that, but then we've seen that this point here, the lower point, is stable, and this one will be unstable, okay? Now, we've also seen that we can reach let's say, conditions of self-ignition, okay, meaning that the system will essentially undergo a thermal explosion. What do we mean by that? We mean essentially that there's an unbalance between the source terms here, so the temperature will grow indefinitely, okay? And the conditions can be reached of self-ignition, for example, if we take this Q minus here and decrease the slope, okay? How can we decrease the slope? Well, we can decrease the slope by, for example, increasing the area to volume ratio, okay? And you can see that if we are over here, okay, the two curves never intersect, and therefore you have always that Q plus is bigger than Q minus, so this is always positive, and therefore the temperature always increases, sorry, okay? What other ways are there to cause an ignition? Well, we've seen the dependence on pressure, okay? We've seen that pressure, especially when the reaction order, okay, is bigger than 1, essentially, we can have a dependence on pressure, okay? But generally speaking, what happens is that you see as the pressure increases, the rate of reaction increases, and therefore we have essentially that this Q plus shifts upwards, okay? So we have something like this. So now, essentially, you still have the same heat loss, Q minus, but you have much more sort of heat produced in the system, and therefore you have a situation where, well, you essentially have a runaway effect, okay, or a positive feedback effect, whereby the temperature always increases, but always remember that at some point the rate of increase of Q plus is much higher than that of loss, okay, of heat, simply because the rate of the heat produced is exponentially related to the temperature, okay? So it will go, the slope will be higher and higher, okay? So it's again, it's a competition between heat produced and heat loss, always keeping in mind that the two are not, do not have the same functional dependence on temperature. One is linear, the other one is exponential. Another way of causing, another way of causing a thermal explosion is the following. So again, okay, we have our heat loss, okay? This is Q plus, well, this is Q plus, this is Q minus. Remember, what we're displaying here on the x-axis is the temperature, okay, in here, okay? It's the temperature inside the vessel, starting from, okay, T0, okay, which is the temperature of the wall, which is kept constant, okay? So what can we do? Well, remember that Q minus was defined as HA over V, T minus T0. So if we increase T0, okay, and we bring it, for example, over here, okay, the slope will not change, but the intercept will. So you see that we have a situation where we are essentially translating this graph of the heat loss to the left. So for any temperature, essentially, you have less heat loss. And when you decrease the heat loss, clearly you're favoring the thermal explosion, okay? You are favoring the buildup of energy within the system because you're not cooling it as efficiently, okay? So again, we said an effect of area over volume, an effect of pressure, and an effect of increasing T0. They all go towards favoring, let's say, the production of temperature and heat inside the system rather than the loss of heat. Okay, and this is where we cause ignition. Okay, so in fact, we're noticing a pattern here because you may have noticed that there is a threshold kind of, but let's do it here. Well, before talking about the threshold, let's just remind ourselves that we have the usual picture of the heat loss, okay, and then a generic Q plus, okay? So what have we learned up to now? Well, that this point is a stable point, right? Okay. So what are the conditions of stability? Okay. Well, let's see. This is the stable operation temperature, okay? Well, first of all, the condition of equilibrium, so remember, this is stable equilibrium. So the condition of equilibrium will be, so equilibrium will be essentially Q plus equals Q minus, okay? I think we all agree, so this point here. But this is not sufficient, because in order to be stable, okay, we have to have this condition here, that the slope of Q minus is larger than the slope of Q plus. So that essentially if the temperature increases, okay, we have a surplus of heat loss, and therefore we're going back because the system cools. And if we have a decrease in temperature, there is a surplus of energy production, of heat production, by the reaction, and therefore the temperature increases and goes back to the equilibrium point. So stability requires that the slope of Q plus, okay, be smaller or at best equal, okay, to Q minus dot. Okay, so this is pretty clear. Okay. So it also means that, well, we're going to define this quantity here as delta T 0. The difference between the operating temperature inside the vessel and the walls, okay? We're going to think about that. Okay. So think that, generally speaking, this delta T0, again, is the difference between the temperature inside the vessel, of the gases inside the vessel, and of the cooling jacket, okay? Now, as you increase this delta T0, it is true that what you're doing is essentially increasing, for example, the cooling, okay? Because the cooling works on the difference, okay? Here it is. The difference on these temperatures, okay? But it's also true that if you increase delta T0, you're also increasing the temperature, okay, inside the system. And remember that these two, Q plus and Q minus, so you're increasing Q plus essentially. Q plus and Q minus are not linearly related, or at least Q plus is not really linearly related. So we have to expect that at a certain point, when delta T is bigger than a certain value, this stability condition will not hold anymore. So let's remind ourselves what Q plus is. Remember, it's minus the heat of reaction QR, the molar concentration of the reactant, the reaction constant, and then the exponential, okay? And again, Q minus is a convective expression of this kind. It's a linear, okay? So what do? Well, we we implement these two conditions. So what about let's do the derivative first. So the derivative of Q plus will be equal to, so let's see, this is dQ plus dQ minus, okay? Will give us something of this sort, e to the RT squared, the exponential of minus e to the RT squared, to the RT, sorry, must be less or equal than, well, let me put H here, big H, okay? And in this H, we have all of the constants, okay? Namely, H, A over V, okay? And then 1 over minus QR, C, and K, okay? So it's a constant. We are considering essentially, well, it contains all of the relative, let's say, constants that we have in the system, okay? The reaction rate, the volume, the area, the coefficient of heat exchange. Well, C is not a constant, clearly. It is for the sake of this analysis here, okay? We're not doing a dynamic analysis, so we can consider C as being a constant. And then K is a constant, okay? Except the activation energy, which remains here, okay, in this treatment. And what about Q plus equals to Q minus, okay? Well, this leads to essentially e to the minus E over RT equals H T minus T0. T0. Okay, so we still have this H here. So if we substitute, so we have 1 and 2, we substitute, for example, 2 into 1, okay? So for example, we can eliminate this exponential here. We have this expression. Right? Which doesn't really mean anything. But again, let's turn it around. Remember that we had defined delta T0, okay, as T minus T0, okay? So for stability, this is the condition of stability, delta T0 must be smaller than T squared over ER, okay? So this, we can call this a condition of stability. Okay, so again, what we thought was going to happen, so there is an upper limit on delta T0 is actually
Professore,
true.
scusi,
Sì.
non dovremmo avere R al numeratore?
E diviso R, scusi, c'ha ragione.
Grazie.
Bravo. Okay. Yeah, keep on noticing this stuff. Grazie. So there is an upper limit on the delta T0 as we imagined. Okay, you can't make it too big. Okay, this different. Otherwise, you're going to have a situation where the condition of stability is violated. It's violated. In fact, when this equals sign holds, okay, then you see that the two slopes, okay, will be equal. Okay, so there's going to be a condition of tangency between Q plus and Q minus. Okay. Another important thing is, look at this. Well, the condition of stability, H, this constant here, doesn't appear. So it seems that it's independent of H, okay? So let's see what's going on here. Again, we have a graph. Okay, we have okay, the stable point, okay, over here. And we have T0, right? So you see that now this is T, okay? So this difference here is our delta T0, okay? Now, what's the sort of the limit of this situation? Well, we can consider two things happening, okay? Remember, this does not depend on H, this condition here. So we can vary H, okay? For example, we can vary HA over V and have it be tangent, okay, at this point here. So now you see that now this is a condition where there's an equal sign here, okay? The two slopes are equal. We could even do something, for example, different. We could translate this upwards, for example, by increasing Q plus, okay? We would still have a condition. So what you're actually doing is essentially you're reaching a condition of tangency. But in any case, this will be the upper bound, okay, of delta T0. So the upper limit. Okay. After this delta T, okay, the system is going to explode. Okay. The system is going to explode because no matter what, Q plus is bigger than Q minus. So you've heated essentially your system too much. Okay. This is actually pretty relevant for a number of things. Okay. You can imagine. Okay. A reactor, internal combustion engines. Think about that. You have a combustible mixture inside the cylinder. Okay. Well, the cylinder is not cooled, okay, actively, but it is losing heat, okay? Think about also this. An adiabatic system would be a system where this Q minus is 0, right? So we would have this sort of graph collapsing on the x-axis, right? Q minus equals 0, sorry, that's supposed to be an equal, is adiabatic. Now, clearly for an adiabatic system, an explosion always happens, okay? So you need an active cooling for the system to be kept in a stable equilibrium, okay? So that's the situation, okay? We have an upper limit on delta T0, okay? Now, does that make sense? Well, what I'd like to actually do is figure out exactly what temperature, okay, I have, at what temperature inside I have to sort of heat up my system, my gas, in order to have an explosion, rather than having this upper limit on delta T0, okay? So how do we do this? Well, let's examine the condition of explosion. So the condition of explosion was delta T0 equals T minus T0 equals, okay, T squared over E over R. You agree? So this is, let's condition, let's write it here, condition of explosion. Okay, so that means that, well, if you rearrange this, it would be something like R over E T squared minus T plus T0 is equal to 0, okay? So what we're actually now trying to understand is what exactly is the temperature at which we have an explosion temperature. So what temperature T of the gases do we need to bring the system so that it explodes, okay? And it seems that this temperature here, this explosion temperature, follows a quadratic, okay? So there seem to be two answers. So let's call this explosion temperature T star, okay? The solution of this quadratic, it would be something like E over 2R, and then essentially minus B, so it would be 1 plus or minus the square root of 1 minus 4 RT0 over E. Okay, so regardless of this expression here, which do we choose? Do we choose the plus or do we choose the minus sign? Well, okay, when we are in these conditions, we have to look at some physical aspects, okay? Now, going back to this graph here, well, this will be the temperature. In this particular case, this would be the temperature that we have of explosion, because there is a tangency condition both in this case or in this case, okay? So this would be my T star. Let's write it here. And you see that T star is in the vicinity of T0. Okay? It won't be thousands of degrees above T0, okay? So we are to expect that for some sort of choice of either plus or minus, well, we should choose the plus or minus solution so that T star remains reasonably close to T0, okay? Let's see what I mean by that, okay? Well, first of all, remember, RT0 over E, remember that E over R is a very big number, always. In combustion, this is invariably true, okay? So you always play around with this high activation energy assumptions, okay? So we are also to believe that this number is a small number, okay? Because of the high activation energy. And this is always because of the Arrhenius number is order 10 or more, okay? So look at this term here. This is a square root of 1 minus, let's call this number, this group here, x, okay? And x is essentially smaller, or a small number, okay? So what we can do is we can actually expand this in Taylor series, okay, around x equals 0. And you have something like 1 minus x squared divided by 2 minus x cubed sorry, no, this is not x squared, this is x linear. And this is cubed. So x squared divided by 8, okay, and so on. Okay, so we are taking advantage of the fact that we are under high activation energy asymptotics. We proved all of that, okay? And so now, remembering that we have, in fact, instead of x, we have RT0 over E, we can approximate this as 1 minus 4 divided by 2, so it's 2x, which is RT0 over E, okay? Minus 4 divided by 8, so 2 RT0 over E squared, okay? And we stop here, okay? We stop at the quadratic term. The rest will be negligible. for this treatment here. Okay. So again, let me just remind you that we're trying to choose whether this is plus or minus. So what do we do? For example, let's take the linear part. Only the linear part. So we're approximating the square root. You can hear me still, right?
Sì, sì.
Allora, we retain only the linear part, okay? And so it's a very crude estimate or a very crude assumption, but let's make this first. So let's go back to our solution T star. And now we substitute only the linear part, okay? So what do we have here? E2 divided by 2r, and then multiplying 1 plus or minus this stuff here, the square root, which is 1 minus 2 RT0 over E. Okay? And let's see. So in case, so this has two solutions, right? We have a plus and a minus side, okay? So if we implement the minus sign, we get a very basic result. The T star is actually T0. So the ignition temperature with this linear assumption is actually, it coincides with T0. The other one is E to the R, sorry, E divided by R. Well, you can see this very, very clearly if you take this term here, you divide, this is E divided by E, and so on and so forth. So E to the R minus T0. If you remember, this would be the activation temperature minus T0. Now, the activation energy, sorry, the activation temperature is really a measure of how big the activation energy is. Okay, it's not a physical temperature, remember, but we can place it and we can express the activation energy in terms of a temperature if we divide by R. And it's a very, very big number. Okay, so you have to imagine it to be thousands and thousands of degrees. Okay, so this in fact is really unphysically larger than T0. Okay, so it would be maybe 10,000 degrees or something. So if we go back here, it would be somewhere over here. Okay, so because we said the activation energy must remain in the vicinity of T0, okay, this is the physical solution. Okay, now that does not mean that T star is equal to T0. Remember, we had come to this conclusion by just retaining the linear part. Okay, now that we've established that the minus sign is the physical solution, what do? We take the quadratic. Okay, we take the quadratic approximation of that root. Okay, don't let me do the whole thing. Okay, you just take, well, I mean, it would be T star equal E divided by 2R, and then essentially 1. We've now established that this is a minus sign, so let me just put the minus sign. And then in the brackets, we have the linear and the quadratic, okay? Minus 2 RT0 over E squared, okay? And if you do the algebra here, we have an interesting result. The T star is equal to T0 plus are T0 squared over E. So now we have a number, okay, for the sorry, can you see the squared here? Let me call this the explosion. Okay. We should probably put an approximate, okay, just to remind ourselves that we are limited to the quadratic here approximation, okay? But it's good enough. It's good enough, okay? So what does this tell us? Well, it tells us essentially a very interesting thing, that given E, well, the activation energy, and given a temperature for the walls, so T0, the temperature, the system explodes at a temperature T. So you have to bring the system to a temperature which is large enough, T star, well, sufficiently above T0 by this amount here, okay? And if it's sufficiently above this amount here, it will explode, okay? And, well, which is interesting, okay? Even for safety reasons, okay? Not that we are concerned of protecting, vessels where you have a flammable mixture, but definitely we are interested in the behavior, okay, of these systems, okay? Remember, I just would like to remind you what we're doing here. We're looking at two particular toy models, okay? The chain branching and the thermal explosion, okay? We have seen that the chain branching is capable of creating an explosive, or giving rise to an explosive behavior where you have a proliferation of radicals, okay? A huge radical pool only if alpha, this branching parameter, is bigger than 1, okay? A little bit like the virus, okay? And the R0 of the COVID virus. On the other hand, we know that combustion reactions are very sensitive to pressure because they follow an Arrhenius kinetics, and therefore there's also the secondary or second mechanism of explosion, which is of thermal nature. So if you don't cool the system too much, the system is hot enough for the production of heat to be predominant over the cooling, and therefore we have a feedback effect where the temperature rises even further, and then Q plus is, because it's an exponential dependence, is hopelessly bigger, let's put it that way, than Q minus, okay? So the heat production is hopelessly much larger than the cooling, and the cooling is not enough, it's useless, and the system explodes in a feedback loop. And we have an expression for this temperature as a function of T0 and E. And interestingly enough, you can also see that it's inversely proportional to E. What does that mean? It means that if the activation energy is very large, okay, for example, it's going to infinity, then the explosion temperature really tends to T0. What does that mean? Well, essentially means that the explosion temperature is lower and lower and lower, and then you have this sort of degenerate case where the ignition, so the activation temperature, the activation energy is so high that the system always explodes, even at the temperature T0, which we can consider as, for example, an initial temperature. That is the temperature of the cooling walls. Okay. We're not considering the case where T is clearly smaller than T0, because then you would have the cooling system actually heating up, okay, the gas inside. So you would always have the system bringing itself to a temperature equal to T0. Okay. So you have a decrease of ignition temperature until you always essentially have explosion, even at a temperature equal to the wall temperature. So even at T0. Okay. Well, again, E is really the key parameter, the activation energy, and it's really a measure of the sensitivity. Okay, this is what you have to think, what it is, of the reaction rate to temperature variations. Okay, so there seems to be a point where the sensitivity is so high, okay, that whatever temperature you have, you could even have a temperature, initial temperature equal to T0, you always have explosions, okay? Because as you increase essentially the temperature infinitely or infinitesimally, you will have a dramatic increase of heat production because of this high sensitivity, okay? We could even illustrate this equation here in another way, okay? Sort of to enrich our view of these things, okay? So let's freeze this for a minute, okay? This relationship here, and let's go back to our system, okay? And suppose that I consider, as I said before, an adiabatic system. So the adiabatic system in this case is a system for which Q minus is always 0, okay? So we are encasing the vessel with an insulation, okay, that doesn't allow heat exchange. So this is what we're doing in an adiabatic system. Okay, so how do we write down the equation of the evolution? Oh, and by the way, as I said before, this is a system that always explodes. Yeah, I hope you agree with that, okay? Because you're not cooling it, okay? So inside you have whatever temperature you have, you will have an exothermic reaction, okay? And so no matter how slowly, so there is an element of time, this is going to build up temperature until eventually this will uncontrollably increase, but it increases all the time, okay? So it always explodes, okay? Because Q minus is equal to 0, okay? So let's write it here. Oops, always explodes. How do we write down the system? Very easy. The system of ordinary differential equations, you only consider the Q plus part, okay? So the Q plus is QR, C is the concentration, K is the reaction constant, E to the minus E over RT. So this is essentially Q plus minus 0, right? For Q minus is 0. And then obviously to this we have to add, if we were interested in the dynamics, we have to add the rate of change of the molar concentration. This is a one-step irreversible reaction, so you have a minus sign C, and then the rate of reaction, which is K, E to the minus E over RT. So that's our system that always explodes. Now, this system, in fact, it's much easier than this. It's much simpler than this. Why? Because it's an adiabatic system. So in fact, there is no exchange of energy, of heat with the surrounding. It's a constant volume, so there is no net change of of work or energy or heat with the surroundings. So we have to think of du equals to 0, right? So the internal energy of the system must remain constant. Okay? What's the measure of the internal energy? Well, CV times the temperature. Now, if I consider the adiabatic flame temperature, I hope you agree with me that this is what remains constant. So this is like the invariant of the system, okay? Clearly, it's the maximum temperature that we'll have, okay? Remember the equilibrium calculations that we did? So CVTA is really the conserved quantity here. So CVTA, when the temperature is equal to TA, it has reached the maximum temperature. So whatever temperature you have lower than that, for example, the initial temperature CV times T0, okay, we would have to add to this the heat of reaction, QR, okay, times the initial concentration, and then dimensionally we would have to divide by a density. If you consider this is an internal energy measured in kilojoules per kilogram, okay, this is generally kilojoule per mole. This is mole, it's a concentration, so it's moles per cubic meter. And this, to get things right, you would have to multiply by a mass, it's the reciprocal of that. So volume divided by kilogram to get kilojoules per kilogram. Okay. So you can think of this as the initial temperature, and this is the chemical energy that will be released, okay, into heat. At the end of the day, okay, when the whole thing is completed, the whole reaction is completed, you're going to have CVTA. But you see that this is always conserved, okay? The internal energy before and after is always conserved, okay? Clearly, this would be an adiabatic flame temperature. We should add at constant volume. Okay, it's not the same thing of an adiabatic flame temperature at constant pressure, remember, because if you let the system expand so that the pressure stays constant, the system is actually losing some energy because it's doing work. It's doing work on the surrounding. Okay, so that would be a little smaller, a little less than what we have here. Okay, these are always things that you need to take into consideration. Okay. Well, so if we can write this for the final state, okay, CVTA, the initial state, CV T0 plus QR. This is clearly the initial concentration, okay? How much reactant you start with divided by rho, okay? We can actually write this for every temperature at every instant, okay? So CVT. This is the current temperature. And then you have a QR. We don't write C0 anymore. We write the current concentration C, which will be less and less as the temperature increase, okay, divided by rho. Rho is a constant in this case because it conserves mass and volume. So this increases eventually, and this clearly will tend to zero, okay? At the end, T will reach TA, and the concentration will be zero. But this is important because then we see that C is not an independent variable. The concentration is not an independent variable because we can write it as a function of temperature. Okay? Which is interesting because this simplifies things even further, because we don't have to clearly, as the temperature is driven towards the adiabatic flame temperature, the concentration decreases. And these two things are related because the internal energy is constant. So we don't have to solve the second equation, this one here, right? We can substitute this value of C in here, okay, and solve only the, I hope you can see the mouse here. I'm just giving it for granted that you can see the mouse.
Sì, sì, si vede il puntatore.
Okay, so if I do that, I'm substituting C into the first temperature ordinary differential equation. We would have plus QR in this case, K, and then CVTA minus T over QR. So that's my original C times rho, and then an exponential. Okay, so you have a bunch of things that actually now go away, CV, and so on. Okay, and even QR. So we're left with one equation for temperature, which is something like this. Okay, it's a nonlinear equation, clearly, with the T here, okay, and a T over here. Okay. We can even do something with this, as we usually do. We can non-dimensionalize this. And the non-dimensionalization quantities for temperature, well, we have the obvious choice of taking T0. So we can rewrite the equation, okay, with a non-dimensional temperature. We're still going to use, don't let me use other symbols, okay? We're just still going to use T. This new T is the old T divided by T0, okay? So you can put a prime here, okay? So this would be prime. And for time, okay, we use, well, think about it. What can we have for time? Well, this is non-dimensional, right? Because it's a non-dimensional parameter. It's energy over energy. And here, because it's a one-step reaction, this is 1 over time, right? So it's Kelvin, essentially, over time here. So time is actually K to the -1 would be an obvious choice, or we can use the whole exponential being to the -1, okay? And so the new time will be the old time, we can call it t prime, okay? Divided by this thing here. Oops, e over RT to the minus 1, okay? So when you want to non-dimensionalize an equation, you take the reference values of, for example, time and of the quantity, in this case, temperature, you divide, you substitute. So now in this case, t prime will be t times t0, and everything will cancel out. So now in non-dimensional form, where again here we're using temperature and time as being non-dimensional, okay? It has an even simpler form. It's TA minus T. So now everything is non-dimensional, the temperatures, everything, the times. And here we can introduce a parameter beta 0 times 1 minus 1 over T, where this beta is just a measure of, it's just E over RT. It's just a measure of the activation energy, okay? I'm just using a more compact form. So obviously the initial condition here would be 1, because clearly the initial temperature, for example, is T0, okay? And so in non-dimensional temperature, it would be 1, okay? So you can actually play around with this equation with MATLAB or whatever you want. You can integrate it with MATLAB and see what happens. And the interesting aspect, okay, would generally be, okay, what happens if we vary beta? And remember that, or the activation energy. Remember this, what we wrote over here. Oh, sorry. Remember the explosion temperature, in some sense, as being a little bit bigger than T0, in some sense, okay? I'll try and sort of convey some intuitive, let's say, notions here. What you should be careful about is that now with the adiabatic system that we're looking at now, we're looking at the dynamic evolution in time. So we're actually integrating the system. We're actually looking at what the system does in time. Before, when we came up with an expression for the explosion temperature, we weren't doing that, okay? We were doing another analysis. We were doing an analysis where we were essentially comparing Q plus and Q minus, and we were setting the two not only equal, but also tangent, remember? So that's a different kind of analysis. It's a steady state analysis, but we can do some sort of parallel between the two. If you integrate this with MATLAB, you will just have to believe me that this is what happens. Well, we have a non-dimensional time, okay? This is the non-dimensional temperature, so we will start from 1, okay? And it will reach eventually a steady state at this temperature TA, non-dimensional TA, okay, over here. You see that if T eventually reaches TA, this saturates to 0, okay? So if you integrate this, you will have this sort of behavior, okay? Where essentially the temperature will remain constant and very close to the initial temperature. at the beginning. And we call this kind of initial time sort of an ignition time. So there seems to be an initial time where the system doesn't really respond too much. Okay, this is where essentially the temperature is quite low, and if you remember, if the temperature is low, the rate of reaction is extremely low. Okay, and this is the main property of this exponential. Okay, the Arrhenius form. But as soon as the temperature increases, because it will eventually increase, because the reactions, even if they're slow, they're going on, so there is a production of heat. At some point, as you increase the temperature, the rate of reaction feeds back, and it's faster and faster and faster until you have an ignition. Now, if E is increased, okay, what you actually have is that this, well, this is just a little bit too sharp, but I mean, so when you increase E, you see that what the behavior is a situation where the ignition time decreases, and you have a steeper and steeper kind of, or a faster and faster reaction. Okay. And well, what happens if E is very large, goes to infinity? Well, essentially, you will have an instantaneous kind of reaction, okay? So you can think that when E goes to infinity, the ignition time essentially goes to 0, okay? What does that mean? It means that, again, try to bear with me with the parallel here. Remember that at the beginning we have the initial temperature is 1, means that in dimensional terms, the temperature is T0. Okay? So what you do have when E is infinitely large, you have that essentially you have an instantaneous ignition. Instantaneous ignition at the ignition the temperature, the initial temperature. Okay. So, and before when E was finite, it was taking a long time. Okay, it was taking an ignition time of finite ignition time. So even though this particular adiabatic system is a system that always explodes, okay, what it's actually telling us, and this is what we want to look at, it's illustrating a little bit the role of the activation temperature, okay? And especially when the activation temperature is very, very high. And when the activation energy is very, very high, an adiabatic system will tend to ignite faster and faster until this ignition time is essentially reduced to 0. And we have instantaneous ignition at the initial temperature. So in some sense, this is equivalent to taking your the analysis that we did before, which was steady state. Okay, it was nothing of this sort, but again, it was relating the explosion temperature to the initial temperature. Okay, plus some sort of term. Okay, which in this case, because the activation energy is very, very large, is essentially 0. So you would have explosion at T0. Exactly what we're having here in the dynamic system, where we have instantaneous ignition. Okay, so it's explosion in the steady state would somehow translate here into instantaneous ignition at T0, at the initial temperature, okay? So you see that the two things actually coincide. This is for E equals 0. Then you could also think, for example, of doing something else. Keep E finite. So E is now finite. Okay. How do we bring the ignition time to 0? Well, if E is finite, we still have this situation here, right? So with an ignition time here, the ignition. So this is E finite, okay? We keep this value of E. What can we do here? Well, we can raise the initial temperature, for example, from 1 to something bigger than 1. So we can increase it above T0. And what you do have in this case, you don't have this increase in steepness of the temperature. That's something that E regulates. But what you do have for sure is an increase, a decrease in the ignition time. So essentially, the reaction takes place faster and faster until, for example, at this point here, you have instantaneous ignition. Okay? At this point here. So again, if E is finite and the initial temperature is bigger than 1, so that means essentially the ignition temperature is bigger than T0, okay? We're really essentially recovering the fact that the difference between the initial temperature and the explosion temperature differs by a finite amount, which depends on the finite value and constant value of the activation energy, which is bigger than T0. Okay, so it ignites instantaneously somewhere here. So T ignition is equal to 0. So for an initial temperature that is bigger than the initial temperature. So in some sense, what we're doing here, again, let me remind you that we're still considering the ignition time to be brought to 0. We're drawing a parallel here, okay? And this adiabatic system always ignites, but it ignites in a certain finite time, okay? So if you bring that time to 0, in some sense, you're shrinking this boundary layer to 0. You're looking at the asymptotic dynamics in some sense, and you're looking at something very similar to what we were looking at before, where we didn't have any time. Okay, we just didn't have any time. So instantaneous ignition equates to a steady state kind of analysis. Okay, this is what you always have in a system that actually explodes. Okay, we may also, there is a program called Cantera. I never have time to illustrate it, unfortunately. It works with Python. It's open source and you can download it. And so if you're familiar with Python, there are a number of very interesting problems that you can solve. And this particular case would be a zero-dimensional reactor. Okay, the vessel here losing energy, okay, whatnot, is a reactor. It can be called a reactor, and it's zero-dimensional because there is no space involved. Okay, so it's spatially homogeneous. Okay, and Cantera will essentially provide with a few lines of code. Okay, it will allow you to actually solve this particular problem. Now, clearly, it will not solve the Semenov system, which is a toy model. It's an oversimplified system. It will actually solve the whole complete system using a detailed chemical mechanism, okay, of the kind that we saw a few lessons back. Okay, so you have to give the system a chemical mechanism. It can be very complex. It can be, a hydrocarbon mechanism with air composed of many tens or if not hundreds of reactions and tens of species. And it will, for each of those, it will calculate both the temperature and the concentration of each species, okay, in time. And the interesting part is that you will essentially also look at, so if we have time, maybe we can look at it, but it's risky because then I have to complete the third part of the course, so I wouldn't want to be too late, and we are late as it is. But for the courageous students who are proficient a little bit with Python, if you have an hour to spare, you can go to cantera.org and download one of the examples, okay, regarding something like this, a homogeneous reactor. In fact, you won't see the equations written down formally. They're written for you inside the program. The actual program is written in C++, but you won't touch that. You will just interface yourself with Python. But there is also a nice program, a nice tutorial or a nice pre-written program where he actually builds the equations, okay? So you can see them explicitly. Okay. Well, let's see. Has any of you heard of Cantera? Oh, by the way, let me just open a parenthesis. Cantera will also do chemical equilibrium. Okay? So you will numerically be able to do exactly what we did theoretically. So if you follow the theory now, you'll really be on top of things, okay? Both for equilibrium calculations and for chemical kinetic calculations, okay? And then there are really more interesting problems. Well, I can give you a glimpse of them. Well, you have reactors that are a little bit more complex than this, okay, that have an input-output. Okay, so we're probably, if we have time, we can look at the equations for these. These are a little bit different now because you don't have now a closed system. Okay, you have a continuous sort of inflow-outflow system. Now, this can be very, very interesting because, and this in effect is, well, the system is called CSTR, which stands for continuously stirred reactor. Why is it stirred? Well, stirred meaning it's perfectly mixed. So you have like a mixer here, okay? Which, well, you have a certain kind of a mixer, okay, that continuously stirs the, so it's, you don't have gradients of concentration. It's always a homogeneous mixture, okay? But the nice thing is that you can feed it with a certain mass flow, okay, of reactant, okay? Now there is a competition between this dynamic that we saw here, this ignition time. It takes some time for the system to ignite, right? But you're also introducing a time scale, a residence time of this of your fresh mixture. So it could even be that this thing doesn't ignite. In fact, it's not even that. It's far more interesting than that. Because it's an inflow-outflow system, and there is a system that wants to react at its own rate, you could have a situation where the system starts oscillating, okay? In some sense. So it goes into a very deep non-equilibrium dynamic. So you don't just have an equilibrium point. You have more complex equilibria where the actual asymptotic behavior of the system, that means the system, the dynamics that will be reached after some time, is as complex as what we call it a limit cycle, for those of you who have done a little bit of dynamical systems. So you don't have a point, okay? You don't have an equilibrium point, which is eventually reached, but you have a continuous oscillation, okay? It's like a ring in a phase space, okay? It's a closed loop. And if you have that, then you could also have some chaotic dynamics as well, okay? So it's a very, very rich possibilities here, okay? And Cantera can also do flames, one-dimensional flames, which is the last part of the course, okay? So, okay, let's see if I have some time. I'll just maybe at least give you a hint, okay, of what you can do with it, okay? Now, we don't have too much time. Let me, I don't know if I want to skip this, but maybe not. So, I think now you have enough mathematical tools to even look at this at this dynamical, let's say, behavior, and think the most adequate sort of mathematical techniques to treat these problems. Again, these are differential equations. We're used to integrating them with MATLAB or something, okay? So that's what we did here. We integrated them. These are the solutions. Bye-bye. We don't care about time scales or anything. If we want to learn a little bit of the inner workings and the dependencies, okay, what does the ignition time depend on, for example, we can try and use some of the techniques or asymptotic analysis techniques that we have already seen in the singularly perturbed theory, or singular perturbation theory. I will just anticipate that next lecture, we're going to also put this system in a singularly perturbed form and try to come up with some form of the slow manifold, okay? And we'll find more or less the same things that we, the same kind of scenarios that we've seen in chain branching. So let's see, what can we use here? Well, I'll give you a variation, okay? So a very, very fast variation of asymptotic theory. Suppose that I'm interested in the ignition time, okay? I want to study this, and I want to, for example, come up with an expression for this. Okay, do I have some expression T ignition equals something? What does it depend on? Well, what we do is we can explore, okay, the so-called temporal boundary layer, BL, okay? The temporal boundary layer is essentially this layer here, the temporal layer, where essentially you have this initial transient, okay? So if you remember in these singularly perturbed forms, what we did is we operate a stretching procedure to time, okay? We dilate time. So what we do is we introduce a new time, okay? Which is essentially t divided by epsilon, where epsilon is a small number. So we're actually dilating time. So that what happens asymptotically is infinitely far away, okay? Well, clearly epsilon must be a small number. So we can choose, for example, the activation energy to the -1. So the activation energy is a large number. So this is, for example, a very small number. Okay? Why are we writing this in this form? Because if we now rewrite the system in terms of this particular stretched time, okay, we have this sort of situation where you have the small parameter here, epsilon, and then the same kind of form for the system. T minus 1 over t, okay? Again, I'm going to skip a few of the steps clearly, because otherwise there's too much mathematics, okay? You can do it. I mean, these are very easy things. In asymptotic dynamics, what we can do, for example, is we can actually take a look at perturbations, okay, of temperature with respect to the initial condition. So we can sort of look at the temperature, which is a function of time, as a so-called regular perturbation, or simply power series expansion, okay, of the small parameter epsilon. So this would be epsilon to the 1, and phi will be the perturbation with respect to the initial condition, okay? And we stop here, okay? So this is a so-called regular perturbation. So this is beta to the -1 times phi, okay? And why are we interested in this? Because we can now essentially rewrite our ordinary differential equation in terms of phi. So we want an equation of evolution for the perturbation, essentially. And well, dt by d tau is nothing else than, well, we can say it's approximately equal to beta 0 to the -1 d phi by dt. Clearly, it's approximately because we're not considering this extra nonlinear terms. Okay? And you get something like this. So we multiply. So we have dt by dt is this guy over here. So it's beta to the -1. Ta -1. Clearly, we're substituting for t this 1 plus epsilon. So it's 1 minus beta 0 to the -1. So it can get pretty complicated. Times e, and then this exponential in terms of phi would be something like this, okay? 1 plus beta 0 to the -1 times phi. Okay? It's quite straightforward to see why this is. Okay, we just substitute this guy here. Okay, and well, we have a beta to the -1 and a beta to the minus 1, so it would be beta to the minus 2. So this is considered to be very, very small, this term, okay? We can also expand this exponent. Again, I'm really going very fast because it's really not very interesting, all the mathematics behind it. I just want to illustrate a little bit the technique. So we can also, whenever we have a nonlinear function, what we do is we expand it, and we have something of this. So you can even think of the quadratic terms of the perturbations to be very small, and so this can be approximated, this term here, as just simply phi. Okay. So at the end of the day, we have a simple equation, ordinary differential equation, which is more or less Ta minus 1 e to the phi. Okay, which has a solution. That's why we simplified it to this form, because now you can actually solve this analytically. So take my word for it. This would be minus logarithm of 1 minus t, Ta minus 1. Okay. These techniques are techniques that were very popular in applied mathematics departments at the universities, where they weren't really interested in the physical problem. They were just looking at interesting physical problems that they could treat mathematically or analytically. So that's why. And combustion is one of those. Okay, so we'd be crazy to ignore all of that applied mathematics approaches. So let me just be in these 2 minutes. And clearly, because we know phi, then we also know the temperature, because the temperature was 1 plus beta to the minus 1 phi. Okay, and so t as a function of time would be 1 minus beta 0 to the minus 1, blah, 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 logarithm of 1 minus time, Ta minus 1, okay? And why is this relevant? Because if we graph, okay, this solution here, okay, as a function of time, you see that it will have an asymptote, because the asymptote will correspond here to the argument of the logarithm to be 0. Okay? So you see we have a T ignition here. So we start from 1, okay, and the system will tell us that there is an asymptote. Now the temperature doesn't clearly have an asymptote, because clearly it won't grow indefinitely. But remember that we're actually looking at the initial transient. So what the asymptote will tell us that this is the actual ignition time, okay, which will have an expression of this sort here, okay. So you see that it can be very, very kind of simplified, you know, the whole theory, if you have enough mathematical tools. Also look at the fact that the activation and the clearly these are non-dimensional parameters, and so we have to revert to dimensional parameters. So remember, this was the non-dimensional time, so we have to revert to dimensional time. And this is Ta over T is 0 minus 1, clearly. This is dimensional. And so we find, essentially, at the end of the day, we can find an expression for the T ignition, which is, if you do the whole, the steps, something like this. So now we are essentially going back to the original variables, okay? And I don't want to steal too much time here, but essentially what we found is that well, T ignition decreases, for example, as QR increases, the heat of reaction, which makes sense. We can't really say too much about the dependence on beta, because remember, the beta much larger than 1 was already used at the beginning, okay? So you can't really tell too much about the dependence on beta, but it definitely, if this is a reaction rate, okay, or actually reaction time, so that can be that can be a measure of the reaction rate. So essentially, the temperature, the ignition time decreases as the reaction rate increases. Okay, I'll get maybe back to this for a few minutes in a couple of days. Okay, but these are the kind of techniques that that you can use. Okay, sorry that I stole a little bit too much time. You can still hear me, hopefully. Otherwise, I'm gonna.
Sì, sì.
Sì, sì, lo so.
Let me stop the recording.